Hello, welcome back to the start of this potentially 2 week long quarantine thing that might go longer. I don't know. We'll see. Um, you'll notice that I'm meeting with you. Hopefully, this I'm looking at red day. This would be Monday, Wednesday, Thursday. On the same note, you white day folks, you'll have folders for Tuesday, Wednesday, and Friday. Um, you feel free to attend either Zoom. I don't really care. They're going to call you if you've got between a 50 and a 65 and you're missing Zooms. But not many of you are there. So if you are, make sure you attend or you're going to get a call. You should be attending. That's the expectation. Um, Remember, I'm not going to quiz this week. I just want to get through some content with the goal being that we then quiz sometime the week of the 7th through 11th with the hope of then taking an exam, maybe 14 through 18, 21, 22. I don't know. We'll see if we're back in person or not. Hopefully having some review days. We'll have some review days. We'll have some quiz days. But kind of backloading these assessments. So that is the plan. You'll have videos up on Schoology soon. Obviously, this is being recorded before the video is posted because this is the video. So that'll be up very soon. So let's get into note 7.1, talking about what is a sampling distribution. And guess what? Not much math today. Mostly qualitative, intuitive stuff today. The next 2 days, 7.2 and 7.3, we will get into the math. We'll get back into normal distributions, normal CDFs. If you still need to make corrections to the 2.5 exam, send me an email, and we gotta figure something out as to how you get corrections done during a distance learning environment. So send me an email. We'll figure that out together, or you can feel free to do it during one of those support times I have. Willing to make Zoom calls, all that stuff. So let's get into the notes though. 7.1. What is a sampling distribution? All right, looking at this notes packet, you see a much shorter glossary, but a very important glossary. Let's make sure. Well, I would make note cards for this. I'm going to say it. I would make note cards for these, and specifically make sampling distribution of a sample proportion and sampling distribution of a sample mean, which extends onto the next page a little bit as well. Those are some of the most important topics. Sampling distribution of a sample proportion, that is basically all of 7.2, and sample mean, that's 7.3, and basically everything else, the stuff that shows up in 7.1 in terms of vocabulary. So we're going to front load you with vocab 7.1. 7.2 is going to be a very short lecture on Wednesday for all of you. And 7.3 will be a longer lecture because there's a new topic, this central limit theorem, and you'll get to watch a video about bunnies and dragons, and it'll just be a great time. So we got to start off though with some definitions. We are setting the foundation right now um, for confidence intervals and significance tests. So what are those things? Those are cases where we want to know the truth about something, the proportion of people that are going to vote for this, the proportion of people with COVID, the proportion of people with hypertension, whatever. We want to know some true value from a population, but we really can't know it, right? Because how am I going to find it? The proportion of everybody that has hypertension. Am I going to go talk to everybody? No, that takes forever. That's a census. It takes us 10. We do that every 10 years in this country, and gosh, sometimes it takes us a little longer. So that's a lot of work. We're not going to do that. So what is a parameter? We're going to take samples, right? But there's a problem with that. So what is a parameter? A parameter is some characteristic describing a population. And check your glossary. There's a little bit more there. The thing about parameters is they're usually unknown. Usually we don't know things like p, the true proportion, or mu, the true mean, or sigma. These are you got to take a census to to know all this stuff. We would need a census. And we don't do a census very often, right? It's you gotta have something really important to be worth doing a census for, like I don't know, congressional reappointment or something. Um, So we usually don't do that. It takes too long. But we're going to have to consider, okay, what do? We take a sample and we get a statistic. What is a statistic? A statistic is going to be, well, let's make sure we write what our statistic. We have in our glossary here. What does it say? A number that describes some characteristic of a sample. Okay, let's underline that, of a sample. So parameters are about the whole population. Statistics are about samples. So what does a statistic gives me? It gives me some characteristic describing a sample. And that's not as bad. A sample, that's doable. A census, not usually doable. So statistics, good thing about statistics is we can know those. We can take a poll. We can get the value. Is it right? I don't know, but we can get it. So a statistic is a known value. That would be like our p hats or x bars or sx's. And you might be saying, what is all this notation? Well, the notation is one of the challenges of this unit. Once again, make sure you're not BSing yourself on notation. Either you understand it or you don't. And if you're just nodding along, when you see that notation, just copying it mindlessly, you don't get it. You have to know what the symbols are. Make some dang note cards for yourself here. How is one related to the other? In statistics, we're going to use the statistic to estimate the sample. Excuse me, not the sample. Parameter. We're going to use the statistic to estimate. We don't know the parameter. I don't know the population parameter, but I can take a sample and I can use that to generate estimates of p, mu, or sigma. So we have down below the symbols, the sample statistic for proportions, for means. We can also do it for standard deviations. The sample statistic is Sx, and the population parameter is sigma. So you can add standard deviations down the bottom of that. What's the big idea here? We take different samples, we get different statistics. Not every sample gives me the same estimate for the thing. Well, what am I talking? Go look at 538. Go look at the poll aggregates for the 2020 election. Not every poll was exactly where it's supposed to be. Some are high, some are low. In general, except you look at Florida. Florida wasn't very good, but most states, the spread was around the truth. Well, why is that? You take different values, you get different samples. Down here, we have this idea of a sampling distribution. The distribution of all values taken by a statistic in all possible samples of the same size from the same population. Here we have the population. And from that population, you take different samples. If 51% is going to vote for Biden, not every poll gives 51% Biden. Sometimes 52, sometimes 49, sometimes 50. There's variability. Not every sample gives the same result. You talk to different people, naturally you're going to get different results. So taking a look at this graph down here, you have your population. You sample from that population. You get different samples, sometimes 40, sometimes 55, sometimes 65. These are like M&M candies. These aren't political opinions, but they're not that different, except that M&Ms don't change color. So population distribution, we have our distributions of sample data, and we have this last thing. This is the new thing. This idea of a sampling distribution. This is like, let's write what this is. All the sample proportions from all the possible samples. That's the new thing. This is like, okay, this is one sample had 15%, and then two samples had 25%, and then three samples had 30%, and then 1, 2, 3, however many. The idea is that each dot on that dot plot, you can think of this as a dot plot, represents a single sample. This is all the samples we could have taken. If we take samples over and over and record the values from all those different samples, in this case, it was just a big jar with some red and blue candies in it. And we take samples over and over and we put the candies back in the jar. We get a spread of values. Sometimes it's low, sometimes it's high, but what do we see in the middle? Here in the middle is the true value, the true population parameter, 50%. That shows up there in the middle, but it wasn't always 50%. Sometimes it's higher, sometimes it's lower. And that's the idea here. This big idea, which hopefully you've written down by now, is that different samples give different statistics, different samples give different values. That's the big idea here in this section today, 7.1. What's the difference between the distribution of a population, the distribution of the sample, and the sampling distribution of a sample statistic? I think this would be a great one to look at the key on. Just to remind you, we do have here a completed set of notes that you have access to. Taking a look down here, what is this? What's the difference between the distribution of the population, the distribution of the sample, and the sampling distribution of the sample statistic? Okay, why do I keep saying this? Because there's a lot of vocabulary here. You seeing that? That's a lot of words that kind of look the same. You need to practice the vocabulary. I'm just going to keep saying it. The population, that's all individuals in the population. The values for everybody. What's the breakdown of everybody? The distribution of the sample gives you the value of the variable for the individuals in the sample. Duh. Here's the hard one. The sampling distribution of the statistic is the distribution of values taken by the statistic for all possible samples of the same size. It's like if we took every possible sample and recorded its the proportion or whatever. Could be a mean. Did that for every possible sample. That's a lot of work. If you have 300 million people and you're going to take 10 people from 300 million, oh, that's a lot of samples. There's a lot of ways you can take 10 out of 300 million. So let's get back to it. The idea here is vocabulary going to be important to you. Sampling distributions of sample statistics. This idea that when we take different samples repeatedly, we're going to get different values. Right. All right. So a father has 4 sons with heights 68, 71, 72, and 75 inches. Determine the sampling distribution of the sample mean height for samples of size n equals 2. Compare this to the 4 sons' mean height. So what's this talking about? So there are many, in fact, there are 6 possible samples of size n equals 2. There's 6 ways we can take 2 of these people. And if you follow my, 1, 2, 3, 4, 5, 6. There's 6 ways. You count them out if you want to. Let's find those 6 x bars. X bar 1 would be 68 plus 71 over 2 is, what is that? What is it, 69.5? 69.5. Great. And then you can do this 6 more times. I'm going to pause. I'll show you the second one. X2 will be 68 plus 72 over 2 is 70. You go ahead and do this for X3, X4, X5, and X6. And we'll see what you've got in a moment. And then calculate the overall average of all 4 of them. Mu, let's do that together. 68 plus 71 plus 72 plus 75. Put that over 4. 3, 4 is 7, and 7 is 14. 14 over 4 is 3.5, plus 68 is 71.5. Great. So we know the overall mean of all these guys. Take a moment. I don't want to sit here and do that. Find the other means. Do a little bit more work there. You find those 6 means, which you can see on my completed notes, and you plot those 6 means, a little dot plot, and you say, okay, well, look at that. The middle of the sample means is the true mean. Oh, I'm going to write that in a funny little statement for you here. the mean of the sample means is equal to the true mean. Think about what that says. The mean of all my x bars, and that's what these are all are up here. These green dots are like x bar 1, x bar 2, x bar 3, x bar 4, x bar 5, and x bar 6. The mean of the x bars is equal to the true mean. That's nice. That's an interesting characteristic, that out of all the samples I could take, the middle sample mean out of all the samples I could take is the true mean. Huh. That seems like an interesting characteristic worth looking at. We'll return to that in a moment. Variability of a statistic. What we're going to see here, as sample size goes up, the variability of our sample statistic, either our x bar or the variability of our p hat, will go down. What's the idea there? Why would variability go down as sample size goes up? As we talk to more people, or we're measuring corn, or we're doing whatever, but I like talking to people. As we talk to more people, we get results that tend, I'm gonna write that word tend and underline it, to be closer to the truth. Debaters in this class are already really good at this, with hedging our bets. Statistics is not as black and white as people want it to be. They want statistics to give it this answer or that answer. We're for sure we're right. And it's not really what it does. It says, well, here's what the models say. Most of the time, this result would come out of that sort of system, but probably maybe there's a lot of hedging in statistics, and it's not as black and white as people want it to be, or as a headline would need it to be to easily convey it. So as sample size goes up, variability goes down. That's the general idea, and we tend to get results close to the truth as we take larger and larger samples. A statistic is called an unbiased estimator if the mean of its sampling distribution is equal to the parameter being estimated. What will that look like? That would be either the mean of the x bars equals mu, or the mean of the p hats equals p. What's the idea here? The middle of our estimates equals the truth. The mean of our estimate equals the true value. And that's what I've written up here in those symbols. But if you don't know what those symbols mean, it's going to be a struggle. Please, seriously. Look at my face. Learn the symbols. Learn the vocabulary. You need to learn the terminology. Otherwise, this is going to continue to be a struggle. If you don't know what those symbols mean by the end of the day, by the end of tomorrow, by the end of the week, we've got problems. Okay. And once again, how can you reduce the variability of a statistic? You can increase n. So you have down below a little example, a free response example. Let's pause for a moment and just let you read through it. Then I'll come back to it. I'll work it together in a moment. All right, so taking a look at this passage, there's a really one thing you had to get from the text. The true value of the population parameter is 75. Okay, so I'm just going to go ahead and draw lines at 75 for all these distributions. Okay, which of the statistics appear to be unbiased estimators of the population parameter, and how can you tell? Well, which ones hit the target? And I say to you that A, C, and D appear to be unbiased. How can I tell that? And why is it not just A? Because most people are very comfortable with A, but C and D also. Well, what's the middle of C? 75. What's the middle of D? 75. A, C, and D appear to be unbiased. The means of those distributions is equal to the true value of 75. Cool. Which statistic, A or B, would be a better estimator? Well, very clearly, you want to know the truth. Well, A seemed to do a better job. A, on average, A is unbiased. It is centered on the true value. What does B do? B tends to over or underestimate. B tends to overestimate. Tends to be high. Look at that. It's up above it. Which statistic, C or D, would be better? Okay, well, that's a better, C or D is a more interesting question. Why? Because C and D both hit the target. While they are both unbiased estimators, there's a difference between them. Like, they both hit the target, but one of them does a better job hitting the target, or rather, one of them tends to be closer to the target. C has less variability and would be the better estimator. The key there being the idea of the variability. If you want to do the Old Faithful example on the next page, you can. If you feel, in fact, I would. There's a key for it. I don't want to talk through it because it talks about very similar topics to this. Maybe you go and try the Old Faithful example. Give this a shot. 2 questions. Look at the key, because I want to keep this video shorter. What effect does the size of the population have on the variability of the statistic? None. Sample variability of the statistic depends on sample size and not the size of the population. And then our last thing for today is something you've probably seen in every science class, but like a Nerf dart gun or something. Bias versus variability. I will draw some little arrows here and some circles, and some circles, and some arrows and some circles. So looking at these, you've got bias and variability. High bias, low variability. Low bias, high variability. High bias, high variability. The ideal low bias, low variability. What do you want? So this is the best. This one probably is the worst. Which one do you prefer out of A or B? Probably B, because it's hitting the target. But if you know which way you're missing, maybe you prefer A. And that's where a statistician has to make a choice. What's the difference between accuracy and precision? How does that relate to bias and variability? Accuracy has to do, that's bias, and precision is variability. This is hitting the target. This is the spread of the estimates. So accuracy, that is, if you're not accurate, you have bias. If you have low precision, you have high variability. So being able to talk about those, being able to visualize those. Usually we don't have it in a 2-dimensional or a polar setting like this. Usually it's in a 1-dimensional linear setting. That's what I've got for you on 7.1. You've got some questions on the back, some essential questions. Take a moment and do those. If you can't do those, you don't understand the vocabulary. Otherwise, I'll see you on Wednesday.